Okay, welcome back to our tutorial. In this section, we'll focus on discrimination, and specifically, we will review four different theories of discrimination taken from from the economics literature. And later, we will look at specific papers and examples from labor markets, online platforms, and education. So let's first start with an informal definition of discrimination. So broadly, when we say discrimination, we will refer to an outcome where members of a certain group are treated differently than members of another group with identical characteristics. And of course, that's a very broad definition and can have different, more specific meanings that we will see next. But the main idea remains the same. So like people who have identical characteristics, but just like belong to different groups, for example, groups defined by race or gender, are treated differently. So in our main question of this tutorial, we are going to try to answer why does discrimination arise in markets? So the economics literature has offered two main schools of thought in terms of discrimination. So we have taste-based discrimination, which arises due to pure preferences and persists even with perfect information. And it's actually based on the principle that decision makers derive higher utility from certain social groups than others. And we also have statistical discrimination, which arises due to imperfect information. And specifically what happens there is that the true attribute of an agent is not observed directly, but only through some proxies. So for example, these proxies can be signals in the economic literature or like features in the fair machine learning language. And we also have other related concepts here like coordination failure and mis-specification that we also see. So the key difference between these two is the effect of information. So if the decision maker had perfect information about this individual, statistical discrimination wouldn't arise, but taste-based discrimination would still exist. So let's start with the first theory, the taste-based discrimination. So in all of these four theories we will review, we will use a labor market setting to keep things simple and consistent. So like I'll hide some details, but I'll give you at least like the general idea of its model. So we have candidate workers in this model who belong to one of two social groups, A and B. And you may sometimes hear me refer to these groups as majority and minority or privilege and disadvantage. It doesn't really matter. What matters here is that the two groups are equally skilled or equally productive. And we also have employers or firms who want to hire workers from this candidates pool. And the decision of these employers depends on their utility that you see on the slide, which they want to maximize, of course. So this utility depends on several factors. We have the price of the product. We also have this function F, which is the production function. And we see that it's actually a function that depends on the number of workers from each group that the employer has hired. And then we have several other things like the wages paid to each group of workers, so WA and WB. And like what's important here is that W and WB are not really constant. So they're actually endogenously determined in our model, as we will see. And finally, we have this taste parameter D, or what Becker used to call it, coefficient of discrimination. Which tries to capture some disutility that employers may have for hiring minority workers. This D parameter comes from a known distribution G. So in total, the utility we see here is a combination of three different things. So like it's a combination of profits from production, right, the first term. Then we have the cost of wages paid to the workers. And finally, the last term is this utility from hiring minority workers. So given this framework, we can ask again, when does discrimination arise? And by discrimination here, we could mean several different things, but we will simply consider that discrimination exists when there is a wage gap between the two groups. Okay. So here again is the optimization problem of the employer. Okay, so the employer needs to choose how many workers in A and B to hire from each group. And observe here a small detail that in terms of profit, so like the first parameter here, so the employer doesn't really care what group here employers belong to. So why this happens? Because the two groups are actually equally productive. So only their total number, as you see in this function, matters, and not actually their group. So the employer's decision must rely on the other two terms in this utility, which in turn means that the employer's decision is much simpler. So actually, it turns out that employers will hire only group A workers or only group B workers, and their decision will depend on this very simple inequality. So we see here that if the wage in this utility per worker in B is actually smaller than the wage these employers give to A workers, then it's best for them to hire only B workers. Otherwise, if the opposite holds, they will hire only A workers. So when this relation holds with equality, we get the indifferent employer. So there is a specific value D star. So remember that D actually comes from a distribution. So not all employers have the same D. So there must be some employer with exactly the D star value that gets the same utility from hiring A workers and B workers. And dividing this very simple relation by WB, we get a nice simple expression for the wage gap between A and B workers. So you may think, okay, we're done, but we're not really done. So like this wage equation is useful, of course, but still doesn't tell us how the wages are actually determined in this model. So remember that wages are actually endogenously determined, okay? So to find out how we get these wages, we can remember that we have several employers, okay, who differ in their taste. And this taste D across employers is described by this distribution G. And from what we saw just like on the previous slide, only employers with taste at most D star will hire group B workers. And each such employer with taste D will have some demand described by some function NBD that we can easily compute by solving its employer's optimization problem. But let's not worry about how this NB function looks like, and just assume that we have it and looks simple. And then what we finally have is that the mass of employers with taste D actually equals the PDF of this distribution. So putting everything together, the total demand for workers is given by the total demand that each of these employers with taste below D star will have. And by the laws of the market, this demand must actually equal the supply of group B workers in equilibrium. So we have demand equals supply. Okay, so like in the end, we end up getting this very nice and simple expression about demand, supply, and the wage ratio. And as you saw, this was pretty much like the whole model. So this already gives us some important properties of taste-based discrimination. So one insight here is that the distribution of the taste parameter D in the population is actually a key factor, but not really the only factor that determines this wage gap. So a wage gap specifically arises when the demand that non-discriminating employers have is not enough to cover supply, and at the same time give those B workers equal wages to A workers. And another important observation here, which I think is quite interesting, is that discrimination on average, and like discrimination on average arises because there's usually a wage gap, is not the same as discrimination at the margin. So even if there was no wage gap, so like if this gap was exactly zero, some employers would still continue to hire only A workers. So why does this happen? It happens because taste in this model creates segregation. So we see that employers hire only A or B workers, but never both, and this will not change in this model. And I feel like that this insight, together with the main assumption that hiring minority workers creates some disutility, are two of the most important critiques of Becker's model. So this was the main example of taste-based discrimination. Okay, so we can now see how Phelps defined his statistical discrimination model that, in contrast to Becker's model, now assumes that imperfect information and not taste and preferences is actually the source of discrimination. So we have the same labor market setup as before, but the model is even simpler than the previous one. So again, workers belong to one of two social groups as before, but they are now characterized by an observable quality parameter Q, which is drawn from some normal distribution and represents some form of skill, potential, or investment in education, anything you want to call it. And in any case, the problem is that the employer can't really observe the skill, so like this parameter Q, but she instead sees some noisy signal of skill. So this could be, like the productivity of a worker, or, an interview performance, or like if we're talking about students, it could be a test score. And this noisy signal theta is actually the sum of the true skill Q and some independent Gaussian noise. So all these distributions you see here may have different parameters per group. So this means that a major assumption that Phelps made, and in my opinion, like it's kind of debatable for many applications that we will see, is that groups might differ in their skill distributions. So like this can happen both in terms of the mean and the variance in the skill. And this, of course, will play an important role, as we will see next. Okay, so the employer in our model cares about skill. So they naturally want to hire the most skilled candidates. So to find out what the skill of the worker might be, this employer will take all the available information she has about the worker. So in this case, this is their group G and the signal theta, and then they will find the conditional expectation of the worker's true skill. And by standard result for normal distribution, we can see that this expectation takes the form you see here. So to understand a little bit how it looks like, the signal theta, so the productivity or the test score, is reweighted by this ratio of precision. So we see the precision of the noise, which is group dependent, over the sum of the skill variance for the group and the noise precision again. And it's also adjusted by a similar term that now depends on the mean of the group skill distribution. So because of all these parameters differ across groups, even if two candidates have the same signal theta, but just like belong to different groups, it is quite easy to guess that the estimates that the employer has about their skill are not the same. But the real question is, okay, like they're not the same, but which one is actually higher? And to answer this question, Phelps considered two special cases. So in the first case, groups have equal variances in their skill and noise distribution, and they just differ in the means of their true skill distribution. So we see that the mean of group A is mu A is actually higher than the mean mu B of group B's skill distribution. And in this case, the skill estimates are actually, as you see in the graph here, two linear functions. So linear in the sense of the signal's value theta. And these linear functions have the same slope, but at a different intercept. So because, very intuitively, because like the mean of group A was higher than the mean of group B, the estimates of group A are always higher than the group B estimates. So in other words, this says that B workers will be considered to be lower skilled than A workers with the same signal theta, and this holds for all different values of signals. And one might say, of course, that this is a rational decision, okay? Because like employers, of course, know that B workers belong to the lower skilled group. And from a Bayesian perspective, like there's really no reason that two workers with the same signal but different group identities should be treated equally by this employer. So of course, from this employer's view and like from an efficiency perspective, this makes sense. But from a fairness perspective now, like things become a little more tricky, right? So like we may easily guess that two workers that had the same true skill Q but just like belong to different groups, will not have the same opportunities to be heard in expectation, which doesn't really sound fair. So we can discuss this in the end. And here's the second case that Phelps considered. Okay, so now the means and variances of the true skill distribution are equal. So the two groups are equally skilled, like we don't see any difference there. But we do see some informational differences. So now the signals of group B are more noisy, which means like more unreliable than group A signals. So graphically, this means that the skill estimates function for the two groups will be two lines again, but these two lines will intersect at the common true skill mean mu. So we see that workers with signals below and above this mean will be treated differently depending on their group. And specifically, B workers with high signals will get lower skill estimates than same signal A workers. And the opposite will happen for B workers with low signals who will get now higher skill estimates than the same signal A workers. So, you know, one may think that this creates a small paradox now in employers' behavior. Okay, so employers know that the two groups are equally skilled, but they still find it optimal to discriminate. And what's interesting here is that, you know, they don't only discriminate, but actually this differential treatment of workers can have two directions. So like both in favor and against group B. Okay, so like this was Phelps' model. And while we're still here in the statistical discrimination framework, let me very quickly jump from 1972 and Phelps to a very recent model that we see in Bohren et al. In 2019. So the idea here is very simple. So we take the exact same model that Phelps used, and the only change we make is that now a subset of employers has what we call belief-based partiality due to mis-specification. So what does this practically mean in simple words? Well, it simply means that this subset of employers have some incorrect information about the mean of some of the two groups. For example, it may be the case that both groups are equally skilled, but these discriminating employers may mistakenly think that the minority group has lower skill on average. And this model tries to capture, you know, like different phenomena, like we could think of it as an attempt to model stereotypes, misconceptions, or a biased blind spot. And I think like it's realistic for some applications that we will talk about later. Okay, so closing this part on statistical discrimination, we now have only one concept left, which is the coordination failure by Coate and Loury. So one way many people view this paper is actually as the equilibrium model version of statistical discrimination, where discrimination arises because different equilibria exist. And what is surprising here, and I really want you to keep in mind, is that discrimination here will arise even though the two groups are ex ante identical. Okay, so like no a priori difference in everything. And specifically in this model, so I'll go slow here. I think this is a very nice model actually. So we have a continuum of workers and workers belong to one of two social groups, again, like A and B, nothing changed here. And what we have in this particular case is that all workers are born unqualified. So some workers may choose to become qualified by investing in education. So for example, like by going to college, but this comes at the cost C that comes from this distribution G for different workers. And we also have, again, like on the other side of the market, we have employers or firms that try to decide how to assign workers to tasks. So they have two different types of tasks. We have complex and simple tasks. And each different type of task gives a different wage to the worker. So we have wage omega, which is a positive value for the complex task, and we have 0 for the simple task. And again, where does the statistical discrimination really come here? And this is why like this model is often considered, you know, as part of the statistical discrimination school of thought. So we see here again that employers can't really observe the skill investment decision of different workers. So instead, they see some noisy signal. So for unqualified workers, workers who didn't make the skill investment, this signal will come from this distribution FU, and for qualified workers, the signal will come from a different distribution FQ. And an assumption here, although like it's not really like a restrictive assumption, but just like for simplicity, we are going to assume that this PDF of the FQ distribution over the PDF FU is actually strictly increasing. Okay, so like finally, the last part of the model is the employer's utility. So their utility depend both on the worker's qualifications and the task that the worker is assigned to. So we see that if a worker is qualified and assigned to a complex task, the employer is happy, so they will get a positive utility. But if they assign an unqualified worker to the complex task, then they will get a negative utility. But they don't really care about workers who are assigned to simple tasks. So like both qualified and unqualified workers give this employer utility 0. Okay, so I told you that we may have multiple equilibria, but we don't really know how equilibria in this model might look like and how really to find them. So okay, I'll skip many details, but the main ideas are here. So we can start with employers. So let's assume that we actually know that at one of these equilibria, a fraction lambda g of one of the groups has invested in skills. And because we are at an equilibrium, when the Bayesian employer sees a signal theta for a worker of that group G, they will use this information about lambda d, so the fraction who has invested in skills, to accurately update their posterior belief that the worker is qualified. So we have this equation that you see here. So where does this formula come from? So we know that the fraction of truly qualified workers in T is lambda G. And from these workers, the fraction who have signal theta and are qualified actually is exactly this FQ theta. And doing the same calculations for the unqualified workers, we finally get this probability. So simple, very simple computations. But like, let's forget the math. So like, let's focus, what does this probability really say in economic terms? So it actually says that there is an informational externality here. So the employer's belief about the qualification of an individual, a particular worker with signal theta, actually depends on the group decision. So like on the fraction of the group that has invested in skills. Okay, so like this is what the employer will do, either we like it or not. And so now they will decide how to assign these workers based on this information. And to make the optimal decision, the employer will look at the table of their payoff, form their expected utility conditional on the worker being qualified or not based on the information they have. So like the signal of this particular worker and the group's investment decisions. And then, okay, like I will not show you the algebra, but then solving for theta, we can find that the employer actually follows a very simple rule. So there is a threshold rule, and when the signal is above a threshold theta hat that depends on the lambda g parameter, of course, they will assign the worker to the complex task and below that to the simple task. So like, if we forget the math here, like this makes sense, right? Like when you see a worker with a high performance interview, you may think, okay, he's probably qualified, I can assign it to the complex task. But when you see a worker with, okay, like not so great performance, then you may say, okay, like it's better not to risk and like assign him to the simple task. So what about the worker's decision? Because like workers also make decisions. So at equilibrium, the worker will know the employer's decision threshold, and then they will also know their personal cost of investment. See, remember that each of them has a C cost. So they will look at their utility from the two options: should I invest or not invest in skills? So it turns out that the employer will find it optimal to invest if and only if this function I that I have here that basically represents the gains from investing and is of course a function of the employer's decision threshold is at least equal to the cost of investing. So there is a trade-off here. And if we plot this function I and remember our MLRP assumption, we can quickly find out that I must be single peak, which will be important. So like we see that it has this general form. And using the fact again that C, as I told you, like comes from a distribution G, we finally have that the fraction of workers who will invest in skill in simply this term here, so G I theta hat. But let's now put everything together. Forget again a bit about what I told you. Like let's look at the bigger picture, okay? So at equilibrium, essentially, we will have two functions. One that comes from everything we said about employers and one that comes from workers analysis. And we need to solve simultaneously these two equations to define two values at equilibrium. So we will have the fraction lambda G of each group that invests in skills, and we will have the decision threshold theta hat star that the employer uses to assign workers into tasks. So in simple words, the first equation that comes exactly from what I told you before says that employers choose a signal threshold, this theta hat star per worker group G, given the fraction of workers that invested in skills in the workers group. And the second equation says that given employer's optimal signal threshold, then some fraction of this worker group G will decide to invest in skills. And combining these two functions together, we will get this final equation here. So what did we learn? Like, except of doing a lot of math. So I told you that this function G, so this function I, that we see here, like in this little cloud, it was single peaked. Okay, so like it had like this form. And because like G is a CDF, so like it is increasing, this implies that in the general case, like this green function here, like this G I theta was essentially like one of the functions we see in our equations here is actually also single peaked. So like it has this form like with the single peak here. And we also like have this other function here. So like this theta hat, which comes from this equation, and we can show that this function is also decreasing. So its inverse also must be decreasing. So by the equilibrium equation here, the equilibria are exactly those points where the two functions intersect, okay? And as exactly in this figure, they may intersect at more than one point. Like here, like the two pink points, which means that there are multiple possible equilibria. So given that there are multiple possible equilibria, why does discrimination arise according to Coate and Loury? So observe that this equilibrium actually, like based on the equation, is actually group specific. So if groups don't talk to each other, so they don't coordinate and just like select different solutions to this equation, workers in each group will make different investment decisions, which means that they will get assigned to complex tasks at different rates, and in the end, they will earn different wages on average. So we see that discrimination is actually the result of coordination failure. So wrapping up this part, let's take a step back now and review what we saw about the different types of belief-based discrimination models. So actually, belief-based discrimination is a term that I borrowed from Bohren et al. And I think like it nicely describes all these non-taste-based models altogether. So to summarize, we saw that belief-based discrimination can arise because of exogenous informativeness differences in Phelps, or be the result of coordination failure, as we just saw, or can arise also from incorrect biased stereotypes of ability due to mis-specification. And for statistical discrimination in particular, so Phelps model, one may see this type of discrimination as efficient or rational. Okay, so like they may think, okay, it's fine because it is actually the optimal solution to an information extraction problem. So what's wrong with it? So like there are actually like two problems. So like the first one is whether it's legal or not. So probably, we're not sure, but probably it's not legal because like the decisions in this model are based on a protected attribute, so like the group of the worker, which is generally not legal in several cases. And also we may see that it's not necessarily fair, but the answer to the question whether it's fair or not actually depends on our views on fairness. So this particular model on statistical discrimination treats equally people with the same expected skill, right? So like it doesn't discriminate with respect to that, but it will treat differently people who have the same true skill. So like we need to think about like broadly, maybe also like in machine learning as well, like whether we want to treat people equally with respect to what we see or what actually is their true skill. Okay, so we are done with the most theoretical part. So now we can move to the more applied section where we will view applications of these ideas in two domains. So we have picked education and online platforms and labor markets here. I'll try to keep the presentation at a high level in this part because really my goal is to just like review recent papers in the econ-CS literature and just like show you how ideas from economics and machine learning can be applied to fairness problems. So given the time constraints I have, unfortunately, I will not be able to cover like everything. I'll actually cover only a small part of the literature. So let's not wait and start with education. So economics has a long line of literature on problems in education. They have looked at, in problems like college admissions, school choice, and affirmative action, where decisions are made, in a centralized or decentralized way. And what's important here and we care about is that explicit fairness concerns are usually not studied in this literature, but we still see some implicit notions of fairness, like the comparison between group aware and group unaware policies and the use of affirmative action. And at the high level, these problems are usually modeled as a market design or an equilibrium computation model. So on the other hand, we have fair machine learning, which also has studied the college admissions problem, but now as an application of fair algorithmic design. And one may wonder, okay, like why ML should care about this application? And one answer to that is that people have started using ML algorithms for admissions decisions, like we see in these news headlines, and I believe we will see more in the future. And in any case, and in comparison to economics, machine learning, as Manish said in the first session, has offered many fairness definitions, but usually has viewed this problem as a classification problem. And it may seem from what I'm saying so far in this comparison, what we are really talking about two separate, totally different worlds. But actually, ideas from both economics and machine learning have been successfully combined in the literature, and we will see some of these examples right now. So there are several research themes related to fairness and equity in education. Of course, we have many papers, mostly in economics, that look at different implementations of affirmative action policies. We also see more recent themes like the role of implicit bias, the use of standardized test scores, and also downstream effects that arise when we impose some fairness constraint. And finally, in the core of mechanism design, we have the notion of strategic agents, and in section 3, Jesse will tell you more about this. So let me first start with a review of affirmative action policies in literature and in practice. So of course, like these topics are well studied, but I think that research-wise is actually a good time to revisit these questions now through a fairness perspective. So many papers in the literature usually interpret affirmative action as a quota rule. This is often seen in ML as well, which means that the school targets a certain fraction of minority students that it wants to admit. And such rules have some very nice properties. For example, they help us achieve simple notions of fairness like demographic parity. But there is a big problem. So the problem is that they're generally illegal. And the same holds for priority or bonus systems that are also considered and can be illegal as well. So for this reason, policy designers in practice have implemented other systems of affirmative action. For example, in Texas and in the past in California, we see that the top percent policies, where the top X% of students from each high school are admitted almost automatically to public universities. And in a similar way, we see other systems that use some geographic proxy, for example, school choice, where students from certain neighborhoods are given some priority. And of course, another potential policy would be exactly the opposite of affirmative action. So a policy that is group unaware and cannot use protected attributes in any way. And that's probably a bad idea for discrimination, as we see in several papers and have already discussed. And finally, we have soft policies like the one we see on the next slide. So one implementation of the soft policies is the Loury rule, which actually says that we must interview at least one minority candidate. And in the literature, this rule has been studied by several papers, and especially in the context of admissions, hiring, and implicit bias. So the main question in this line of literature is this. So in the presence of unconscious bias, when the observed merit of minority candidates is distorted in some way, how can we improve the decisions? And one particular case where the observed merit of a minority candidate is distorted is when there is some multiplicative bias. So instead of observing this true skill Q that I was telling you all the time, for minority workers, we actually observe Q over beta, where beta is this implicit unconscious bias. So when Loury rule is applied to settings with implicit bias, it can improve fairness and at the same time, the decision maker's utility. So moving now to a completely different topic, a part of this literature has started looking at the role of standardized test scores in the question to drop the standardized testing requirement or not. So the question to drop standardized tests is actually very timely. For example, we recently saw that University of California permanently dropped the testing requirement and announced that they want to design their own test instead. So the use of standardized tests in admissions is an old and difficult debate. And on the one hand, we have people who say that dropping test scores might lead to statistical discrimination type of effect, like what we have seen. But on the other hand, there are certain access barriers for students that we can't ignore. And these barriers come in terms of the access to the test and other things. So these two factors essentially create a trade-off between informativeness and access to the test and lead to the main question of the paper, which is how will dropping test scores affect academic merit, diversity, and individual fairness of the admitted class? And to answer this question, we can construct a multi-feature statistical discrimination model with a continuum of students who apply to a school which has some capacity constraints, so they can admit only a small mass of students. And as in the classic statistical discrimination model, same idea, there is a true skill that cannot be observed. But the assumption here, in contrast to Phelps, is that both groups are actually equally skilled. The difference with that model is that now instead of one feature, we have multiple features. So each feature is theta k. One of them can be the test score. And again, these features are the sum of the true skill Q and some noise. And the noise parameters can differ first across different groups, but also across different features. And one important convention that we make here is that Group B students face an informational disadvantage, which means that the total precision we see in the features of Group A students is actually higher than the total precision we see in the features of Group B students, okay? So again, as in what we have seen, the school will observe the group and available features of an individual applicant and estimate the skill of that student. And what happens here is something new. So the school will repeat this process for all applicants. So at an aggregate level per group, the school will eventually get a perceived skill level distribution per group now. So this is the distribution in the second box. And here's what happens when the school uses this perceived skill distribution to make admissions decisions. So even though we started from identical true skill distribution, so both groups are equally skilled, and the school is Bayesian, our assumption here on the informativeness difference between the two groups leads to a lower variance in the aggregate perceived skill level distribution for group B. And specifically, the higher uncertainty we had in the features of group B students leads to more conservative estimates for their skill at an aggregate level. And as a result, in this picture here, we see a greater concentration around the mean for their estimates compared to group A estimates. So when a selective school comes and sets an admission threshold, okay, so like here, more group A students will be perceived to be high skilled, and as a result, more of these A students will be admitted to the school, which naturally means that group B students are underrepresented. So the main takeaway is that when we drop test scores, so one of the key available features, the test scores and other features variance really drives all the results and can actually have an ambiguous impact on disparities. So we can see that dropping test scores may sometimes lead to a less diverse, less academically qualified class. But as we see here in this figure, there is actually a trade-off with access. So if there are sufficiently high barriers to testing, then dropping the test score may actually improve both metrics, so like both diversity and academic merit. And of course, like there are several open questions that remain, we can consider other types of barriers that induce inequity. And more broadly, we can think about how to use like this conceptual framework and statistical discrimination in general to study other fair ML questions. And I want to point you to this paper as well, who also looks at test scores, but the question of taking the test multiple times. Okay, so finally, another interesting and quite unexplored direction in the literature is understanding the long-term impact and downstream effects of fairness constraints. So Cannon et al. Study a two-stage model here, where we see again some familiar ideas from statistical discrimination. So colleges observe a test score for each student and admit the students with the highest estimates. And then the admitted students finish college and go on the market, and there the employer will use their college GPA to hire some of them. Okay, so in this two-stage model, the paper asks whether we can achieve two different goals. So the first goal is equal opportunity, which means that the probability that an individual student is admitted by the college and then hired by the employer should not depend on their group. And the second goal is to actually eliminate what we call downstream bias, which means that employers ideally should not make hiring decisions based on the group of the college graduates. So the main takeaway of the paper is that both goals are actually feasible only in the trivial case when the school doesn't report grades or the skill is perfectly observable. So when grades start becoming informative, then these goals are generally unachievable. Okay, so we are done with the education part. So we will quickly move to the next pretty exciting application and the last application, which is about online platforms in labor. So again, we have several research topics in this very recent literature. So I'll talk mostly about the second one here and just briefly touch upon dynamic effects. So I will not talk about hiring, although this is also a very exciting area, of course. One particular application is this paper by Freshman and Pavan, who look at soft affirmative action in hiring practices. So we see again these ideas from Loury, rule, and so on. And finally, we have some literature on automated hiring algorithms, which poses a different set of more algorithmic challenges. So let us just look at online platforms. Okay, so online labor markets indeed have many of the problems of traditional labor markets, but there are also several things that work quite differently in online spaces. So at a high level, the big difference is, of course, the presence of a centralized platform, which makes design decisions, sees users' information, and even influences the decisions of the users in a direct or indirect way through all the systems. So like through review and rating systems, search, ranking, matching algorithms, and recommendation systems. So the pricing system may also play an important role in this labor markets. So we saw that all these models for markets, for traditional markets, actually had an employer who set the salary. But in an online labor market, workers might need to set their own hourly rate and give a part of their income as a fee to the platform. For example, TaskRabbit used to have this scheme in the past. And of course, other factors like the platform's own incentives to maximize revenue, this ephemeral nature of some gig economy jobs, and on top of everything, like, and very importantly, the fuzzy law framework around these new markets create a very complex picture, and most importantly, a very different setting for researchers. And since we don't know as much about it as the traditional labor markets, we can start with the most basic question. So, does discrimination really arise in online labor markets? And if so, why? So, we don't have a good answer to that. But here is some empirical evidence that helps us get a preliminary idea. For example, on Airbnb, applications from Airbnb guests with African American sounding names are about 16% less likely to be accepted compared to identical guests with white sounding names. And we also see that this discrimination decreases even with only one review. So we see that information has a positive effect, which makes us think that, okay, like we may have to deal with belief-based discrimination in this case. And one particular explanation for the behavior of the users could be the proposed theory of mis-specification that we briefly discussed in the first part. So this paper by Bohren and others study through theory and experiments how evaluations in these platforms impact discrimination. So in the paper, they consider, like all types of discrimination we have seen basically. And they find a pretty interesting observation when evaluators are Bayesian. So they find that reversal of discrimination might happen, and this is only possible when mis-specification exists. And what's particularly exciting here is that they actually empirically observe this reversal phenomenon in their data. So in the second paper here, we see an online labor market model this time, theoretical work where employers rate workers and at the same time learn from past reviews. So again, this paper adopts the mis-specification theory, but for naive learning. And it means that some employers hold mis-specified models about minority workers, which eventually leads to discrimination. So finally, like closing this section, I would like to conclude with several open questions for online labor markets. So although platforms already collect data and seem to be interested in implementing policies that reduce discrimination, there are definitely like very important legal concerns and constraints. So it is still a challenge to design legal policies that do not harm the market and still reduce discrimination. Another question is how can the platform decisions for search, ranking, pricing, and recommendation system can affect discrimination? And I think this is a series of very interesting questions in the intersection of operation and fairness this time that we can start looking at. And finally, I think that if we really want to solve these problems, we need a research framework potentially described by some of the models that I talked about today to better understand the interaction between human bias and bias coming from platform decisions, and eventually distinguish between the two. So thank you for your attention. I would be happy to answer any questions.